We hear about AI like ChatGPT all the time, right? But have you ever stopped to wonder how it actually learns? I mean, it's not like it's reading textbooks. It's something way more fascinating, built on math and a whole lot of data. In this explainer, we're going to pull back the curtain and build our understanding from the ground up, from simple data points all the way to generating human-like language. All right, so here's our roadmap. First, we're going to tackle the fundamental problem that all AI is trying to solve. Then we'll introduce the star of the show, the neural network. After that, we'll see how you actually train one of these things, how that gets us to understanding language, and finally, we'll peek over the horizon at what's next. So, first things first, before we can build any kind of AI, we really need to wrap our heads around the core challenge it's designed to overcome in the first place. I mean, this is the big one, isn't it? The whole point is that we don't want to sit down and write a million if-then rules for every possible situation. We want the machine to figure out the rules for itself just by looking at a bunch of examples. But how do you even get started with a problem like that? Well, it all boils down to something that looks a lot like this: finding a pattern. Imagine these dots are data, maybe house prices versus square footage. The goal is to draw a line that predicts the price. But look at the two tries here. The blue line is way too simple. It's just a straight line, and it totally misses the actual trend in the data. But the wiggly red line? It's too complex. It's not just learning the trend, it's memorizing all the random noise, too. This tension has a name, and it's absolutely central to all of machine learning: the bias-variance trade-off. High bias is that simple blue line. We call it underfitting. The model is just too simple to capture the truth. High variance is that crazy red line. That's overfitting. The model has learned the noise, not the signal, and it's going to fail miserably when it sees new data. Every single learning algorithm is basically trying to find the perfect balance right between these two. So, how do we find that balance, especially with really complex data? Let's move on and meet a new kind of model that was created to navigate this exact challenge and learn some incredibly complicated patterns. So, what exactly is a neural network? The first thing to do is kind of get the image of a literal brain out of your head. It's much more accurate to think of it as a really powerful and incredibly flexible computer program built out of layers of interconnected mathematical functions. Here's the basic idea, and don't worry about the math on the screen, just focus on the flow. The network takes in some data, that's our X, and it passes it through a series of layers. It's kind of like an assembly line. Each station, each layer, does a little something to the input, transforms it a bit, and then passes it along to the next one. The entire network, from start to finish, is just one big, complicated function, f of x. Now this is where the real magic happens. A network with just one layer is pretty limited. It can basically only learn to draw a straight line. But when you start stacking these layers one on top of the other, the network's power doesn't just improve a little, it explodes. It gains what we call depth, and that depth allows it to learn the kinds of complex, curvy, non-linear patterns you need to recognize images, understand speech, or even write a poem. Okay, so we have this really powerful program, but when you first create it, it's a complete blank slate. It doesn't know anything. So how in the world do you actually teach it to do something useful? Well, the training process is actually a surprisingly simple loop. First, the network makes a guess. Step 2, we measure how wrong that guess was. We calculate its error. Step 3, we make tiny adjustments to the network's internal numbers, its parameters, to make it a little less wrong next time. And step 4, we just do it again, and again, and again, millions or even billions of times. But how does it know which adjustments to make? That third step is the absolute secret sauce. We use this brilliant algorithm called gradient descent. The goal is to make the error as small as possible. You can think of it like this. You're standing on a huge, foggy mountain, and your job is to find the lowest point in the valley. Gradient descent is the math that tells you which direction is downhill from exactly where you're standing. Now, making this whole process work for the massive networks we have today was a huge challenge, until a key software innovation came along called auto-differentiation. Honestly, you can just think of it as a compiler for learning. It automatically figures out all the complex math needed to find that downhill direction, making it possible to train the enormous models that we see today. And this chart illustrates the whole thing perfectly. We can literally watch the network learn in real time. The blue line, the training loss, shows the error going down on the data it's already seen. But the red line, the validation loss, that's the one that really counts.
That shows how it's doing on new, fresh data it's never seen before. The entire goal of training is to find that sweet spot, the lowest point on that red line. That's our best model.
All right, so we have a pattern-finding machine that we now know how to train. The next question is, how do we apply all of this to something as messy and complicated as human language? The first big leap is to recognize that language is a sequence. The order of words matters a lot. The dog chased the cat is completely different from the cat chased the dog. So the task gets reframed into what's called sequence modeling. Can the machine predict the next word in a sentence given all the words that came before it? Now, early models called RNNs tried to do this by reading a sentence just like a person would, one word at a time, but they had a terrible memory. By the time they reached the end of a long sentence, they'd pretty much forgotten what happened at the beginning. And then came the breakthrough, the transformer architecture. Instead of reading sequentially, it's like it has a bird's eye view of the entire sentence all at once. This allows it to understand the relationships between every single word, no matter how far apart they are. Sure, it's computationally way more intensive, but this attention mechanism is the core innovation that powers models like ChatGPT. We have come an incredibly long way, from just drawing lines through data points to building systems that can write entire essays. So what's left? Where are we headed now? The work is far from over. Researchers are still perfecting transformers. But the next major frontier is moving beyond just learning from static text. The focus is shifting to reinforcement learning. You can think of it like training a dog with treats. The AI tries an action, and if it leads to a good outcome, it gets a reward. It learns by trial and error. You combine that with powerful search, and you start to create agents that can plan and act in the world, which is exactly how the AI AlphaGo mastered the game of Go. And that brings us to our final thought. We have created a tool that can learn patterns from almost the entire library of human knowledge and language. The fundamental question is no longer just how these machines learn, but what we, as their teachers, choose to show them next.